Hello, and thank you for joining me. You're here with Data Science Teacher Brandon, and we're going to be doing a level 6 computer vision project. And this was kind of just, or I shouldn't say just about, but it's more about setting up experiments. So we're going to do, I think, something kind of fun for the computer vision project, the computer vision scientist, but we're also going to do work using a class to set up and use that ability in with Python to kind of enable our experiments, make it a little bit easier to set up experiments and testing kind of a wide range of possible hyperparameters for our neural network. Okay? So to get started here. So importing our Google Drive here. And just importing the standard data science libraries that we all love. Pandas, NumPy, TensorFlow, Matplotlib, Seaborn, and we're going to use, because it's a computer vision project, we're going to use a CV2. And simply we're going to use this a little bit of the importing of the images, but also to do some of the pre-processing that we're going to set up today. So this data set is just too big for me to put on my Google Drive, or sorry, my GitHub reservoir. So I had to import it from my Google Drive. If you want to go to this website, I'm sure I put a link on the post, and I'm just going to put hopefully I did, put the data on the post as well, so you can get easy access to that. But it's easy enough to go down to these websites, so just download it from there. If you want to, and then you can submit in the contest to use this. But this will work on any MNIST data set that you have. Well, yeah, any image MNIST data sets. Okay. So we're going to import the two data sets here. We're importing just the DF and then DF test. The DF test is what I'm going to use for the final predictions and the computation. So what this layout is 40,000 for the training and then 20,000 for the test. To just notice here, what I'm doing here is I'm going to save the index values for my project later, or sorry, for the test prediction. So the way it works, it wasn't using Python indexing, it was just using regular starting at 1 instead of starting at 0. So I'm doing df.index plus 1, because then this will line up with the index that they're using for their predictions. Okay, so we're going to just saving that for later. Highlighting that we're doing that. I didn't know that at the beginning. I came to that. Here's a little bit of reading if you guys wanted to do on what we could do for pre-processing. Some different enhancements in general sense of what we could do. So I'll like, yeah. Okay, so here what we'll do is try a whole loop. So what we're going to do is we're going to loop through this and plot. And let's just start by looking at the images as they are. Okay, so we're going to go for n in range. This goes 0 up to, but not including 10. So 0 to 9, which is perfect for our data set. We're going to go NumPy, and we're going to put this into an array. We're going to go df, and then inside this, we're back to do logical indexing. We're going to go df.iloc. If it's equal to the first column, if you look at the data set, the first column is the target, and then everything to the right of that is the actual image, the pixels flattened out. Okay, so we're saying if the first column, so all of the rows, comma, first column, so column 0, is equal to n, what we're going to do is we're going to select all the rows that are equal to that, and select everything from the second position, second column, all the way to the end. We're then going to go reshape. Okay, dot reshape. This is one of the reasons we're putting it right into the NumPy array, because we can just do this dot reshape and 28, comma 28. Okay, I've done this a few times. I remember that 28 by 28. It's a pretty common shape for pictures. Okay, after we do that, we're going to go plt dot subplot. And what we're doing is we're saying it's a 4 rows, 3 column plot, and then in this position, we're going position +1 because it's 1, 2, 3 in the way that this grid works. Okay, so this is going to say in the first, in the second, and the third, position up to the 10th position, sorry, number 10, we're going to put the other image in. So let's just go through that. It's going to loop. Then what we're going to do is axis.im show. And we're going to go im set title and then ax axis. And then after this is all done printing, we're going to go tight layout and then t.show. Let's run this and see if it's correctly. Oh, I got an error. Oh. on the last part. What did he say? We printed the plot. Okay, so there we go. So go to that. Okay, so we'll do a little bit less. So this time we're going to look at doing the Gaussian blur. So this is one technique that we can do to. This is not one of the ones that I ended up choosing, but this is just showing this might work in other situations. So here we're just going to do as type and then numpy integer 8, so this the smallest, I guess, space taking data type, okay, that we can do. We're going to set the kernel size 5 by 5 to the Gaussian calculation. The sigma, which is the average, or sorry, the standard deviation, I apologize, to be 1, and it's going to use this to essentially it's trying to clean up the noise. It's trying to use this as a parameter to clean up the noise, not as a Gaussian blur, but as blur removing. Okay. So what we're going to do is we're going to go cv2 dot Gaussian blur. So we're going to put in here the image. Put in the image, and then these two parameters right up here, we're going to put the kernel size, and then sigma. Okay, so this is, and then we're going to do the same thing that we did up above, plt.subplot, not subplots, subplot. And then we're going to go im show, and we're going to do the all important tight. You don't need tight layout, but if we're doing these multi-plots, it kind of just puts them in unorganized and just kind of, it just cleans it up. It really kind of organizes and make sure this is kind of in alignment you would expect it to be. Okay. So here we go, and so it is again. It's to get rid of noise. I feel like this kind of blurs the edges though. And that's kind of something that we would find. In part, I find this one didn't help, and so my suspicion would be that because it kind of blurs, it gets rid of the noise in the sense it smooths out the image. We almost wanted something the opposite of this in our file. Okay, so this just didn't seem like it worked that well. Because again, the blurring, it cleans it up. I guess it gets rid of the noise, but we almost want something that not brought out the noise as the correct word, but defined the edges a little better. That's actually one of the ones that I used. Okay. So in the next one, we're going to look at setting up the threshold, and this says everything above a certain point you'll keep in there. Everything above goes to one side, and everything below goes to the other side. So really just changes it into two colors, but we'll do the reshape again. And really just defines, you kind of define where that limit is. Okay, so we're going to do the same thing. Dot as type. Dot as type. So in the first one here, we select out the image, and then everything from the first row, we're going to dot values, turning it into a numpy array, setting the data type to float, reshaping it. And we get the as type, I'm going to set it to a very low data type. Works better with this algorithm. And then we're going to go into the next part. So we set our threshold value, our max value, and what we're going to do here is we're going to go CV2 threshold. Okay. So like we did before, kind of the same syntax. Usually the other side the same syntax. We're going to put image in first. We're going to set our threshold value in the variable we just assigned up above. We're then going to put threshold value. We're going to put max. And then this in capital letters here, we're setting just a natural from it, thresh underscore 2, all capital letters. Okay, we're going to do that plt.sub, and just notice here we're doing, there's two outputs. We're not using one of the outputs here, we're just looking at the cleaned up image. Okay, we're going to do plt.subplot, subplot, not subplots again, and then im.show, or ax.im.show, and there we go. Okay, so just doing the threshold on this one. So the threshold value and the max value, which is just 255. Thrash. Oh, and I forgot, you know what it was? I forgot to H here. Oops. H. Gotta make sure you spell it properly. English. That's important, even in coding. Okay. So we got that one done. And you can see, so really what it's doing is just making sure anything below this variable right here, you can play with this. 127, I put it just right in the middle, is going to be white or black, I guess in this case, and then the other value is going to go up to the dark side. You can see you don't get the texture anymore in the stroke. It's all just been pushed all the way up to the top. Okay, so this could work. This could be valuable. I didn't end up using that one either. I like this one, the histogram equalization. Okay, so if you look at what this is trying to do, this is trying to essentially, lots of times, lots of the pixels are concentrated in one area in terms of the brightness or the intensity of each pixel. So what it does, it tries to spread it out, not necessarily blur anything, but it starts to put everything in a wider range. And I think this kind of helps with the model because it just gives it a little bit more. You can see essentially more detail. It's not kind of all crunched into one pixel area. It's kind of spread out. So the weight is really just spread out. Yeah. And this, we're going to give it the equalize, hit capital H, hist. Okay, there's not any parameters we need to give this one. Do the same thing, the reshape on the dot values as type. We're going to set the type, the data type afterwards, make it even simpler, or use less space. Okay, and then just right here in the bottom, we're going to go tight underscore layout. Oh, I spelled it like English person instead of American. Do the Z. I'm from Canada, so I don't know why I spelled it that way, but anyways, and so this is one of the ones that I used. Really, again, this is just spreading out instead of having all of the intensity values concentrated in one area. This is kind of spreading them out to some extent. Okay, so and I think it worked well. Okay, so here we're going to do, and I also really like this one right here, setting the edge canny edge detection. Okay, so here what we're going to do is we're going to go CV2 again. So we're doing the reshape, doing the data type change, CV2, and then we're going to do the canny function for this. Okay, we give it the image, and then we're setting our lower threshold and our higher threshold. And what I just kind of choosing, you can play around with these numbers, kind of just spacing them equally in the range of data that we have, and then 80 and 160. So anything below 80, this is going to be able to find kind of the numbers in the middle and highlight these, and this should hopefully give us defined edges, which are usually not the most intense patterns, and kind of somewhere in the middle is kind of the idea behind this. Okay. Here what we're going to do is we're going to do set title, two T's, and then access in the next one, and then the last one do plt.show. And so here we get nice, really kind of highlighted edges and stuff. And I think this works really well. What we're going to do is we're going to put our data into essentially two branches in our neural network. It's going to take and dissect these two images. And this will then be able to highlight. I think this one worked really well because it highlights kind of the edges. And this, the hist equalization, what I liked about it, or my theory is to why it would work well, is it shows a lot of the detail on the inside. You can see here, you can actually see a lot of the intensity changes. You see a lot more detail in the inside strokes. I don't know, I thought it was kind of very different styles of pre-processing. I thought using those together might give us a good answer. Okay. So here what we're going to do is we're going to make our labels and images to train our training data set. Okay, so here what we're going to do is df.ilog, selecting them out, and we're going to go select from the first row or the second row, so row number 1, values dot reshape. And then what we want to do, this is kind of an easy little trick. We don't really want to reshape the number of rows. We want the rows to be included in this. So -1. And then we're going to do everything else. We're going to do 28. 28. Okay. This is going to make the same number of rows, but then we're going to make squares out of the next shape. So this is going to be a NumPy matrix now in 3 dimensions versus just a square 2-dimensional data frame. Okay, so can't really use like a data frame anymore, but that's why we have NumPy for these more complex dimensions. Okay, and TensorFlow as well. Okay, so here we're going to do NumPy. So we're going to do get underscore dummy. So we're going to do the one-hot encoding of our target ahead of time, just to make it easier for a model, so it doesn't have to do that transformation when it's doing the processing. So we're going to go ilog. We're selecting just the first column, so column 0, and then we're going to get the values after we do this. So we're going to get dummies of that, and then we're going to get just the values, just to turn this into a NumPy array. Make it go truth a little bit faster. Almost noticeably faster, you can see that, and I forgot to do values. Get dummies. Ooh, bad at spelling today. Okay, so then we have, if you want to look at the labels right here, you can see we have our row now, our targets, and this would be the second class of number 1, because it would be 0, 1, be this position right here. This would be our target, and this will allow for the linear algebra to happen to be able to do the matrix multiplication on the inside as our model is training. Okay. So here what I've done is I've set up the hyperparameters for our network today. So we're going to do convolution, want our convolution activation, our pool size. We have our convolutional kernel right here as well. So 4x4, 2x2, dropout layer right there. We have our dense neurons, our dense activation, our head dense layer. So you have one kind of, I have a dense layer after both of the pre-processing, and then one more as they combine, one more after the combination, to really get the emphasis and the texture from having both of those together. Okay, or the decomposition of those together. Okay, so then I'm doing another exponential linear unit after that. Okay, so here what we're going to do is we're going to do the convolutional block first. Okay, so here what we're going to do is we're going to create our convolutional block and make our code writing a lot shorter. And we're going to be using this basically directly in our function. So we're going to create this before so that we use it inside of our class that we're going to do to create our experiments. So we're just going to focus really on lots of the building of the algorithm, and then the architecture, the overall, the bigger architecture we'll build there. But we're also going to worry about the experiment, the training, and the predictions of the model. Okay. So first, what we're going to do in our convolution, we're going to do cov 2D to capital B. Then if you notice here, we're going to put in our first one, we're going to go filter. So I just, a really simple way to use my variables, keep them kind of smaller, is to just get rid of the values. It's kind of my rule. So this is filter equals our cog filter, and that's how many planes, how many extra dimensions we're going to create. And you kind of think that each dimension might capture one pattern, or each plane each filter might capture one pattern. Okay, so not exactly neurons, but they kind of almost like their dimension, another plane. It's a square object, but it is kind of like a neuron in the sense that it's going to try and capture a pattern in that square grid. Okay. So we're putting the filter though in the cog filter. We're putting the second one is the kernel, so KRNL, into the second position, which is the kernel. To define the kernel, our activation is then going to be our acts. This is going to essentially just take it. We're going to be given the output from up above, and we're going to be taking it, and it's going to go just with our functional model. So just the multiply type of thing, this function multiplied by this function. Oh, that really means this is happening, this function is happening inside of this other one. It looks like multiplication. So the next one's going to cov 2D again. filter kernel activation. We're going to multiply x1 into this value here. So just continuing down, we're going to do max pool to d, and then we're going to do pool size is going to be equal to pl underscore sp. Just getting rid of the vowels in that variable right here, but it's our pool size, so it's going to be setting the pool size, and then this is going to be setting a dropout. And not a surprise here, our dropout is equal to dropout for the convolution. So show you the bracket there. Okay, and that's going to be multiplied by 3, and then we're going to be returning the output of the last variable. Okay. Now we have our convolution block, and now this will allow us to repeat this a couple times over very quickly and easily. And I need to just run this first. Make sure these variables are initialized. What happened was I haven't initialized these variables, so when I'm saying it's equal to this, it's like equal to what? It's not nothing. That's not anything that we know about. So here what I'm doing, this is actually very similar. I left this. I didn't really do this because we did this. So I'm not really doing anything different here, but what I'm doing is I'm going to pre-processing this. I'm going to go for the images, all of the images in our images, our list of images. We're going to pre-process it. We're going to do equalize hist. We're going to expand the dimensions. So we're just going to take in the raw images, and we're going to do two types of pre-processing together. So we're going to do the equalize hist, then we're going to do the canny pre-processing. But it's exactly the same thing that we did up above. The only thing different here is that I'm adding this expand dimension right here, and that will just allow for the convolution to happen in the neural network. Just because it's one dimension, like it's black, but convolution normally expect 3 color grids, would be more typical, I guess. So even though when there's that one, just one of that other dimension, it usually just doesn't acknowledge that. So we just have to say, hey, there's only one plane of color, one channel of color, but it's still there. It's still a dimension. Okay, that's all that's really doing here. And then just our divide by 255 as well. So we go through all of these. So going through all of our dimensions and then putting those into an array. And then we'll be returning printing those out as array, which is the shapes, but then I'm printing or returning the equalize hist and then the equalize can, then the can edge contrast color function. So this is the little function preprocesses. You're going to loop through preprocess 1, loop through preprocess the other. So pretty easy. Okay. So now we get into defining a class. Run this actually above. Okay, so let's define our class. So we're going to be defining a class called model express. Let's call this class. And inside our class, we're going to be defining a function. So define, and this function is going to be, this is the init function. So it's underscore, but it's underscore underscore in its is initialization underscore underscore. This is kind of saying all of the variables that we're going to put to this self argument, and we're going to use this self variable that we create here to be passed, basically allow us to packet all of the so many different variables that we can use to train our model, hyperparameters, our inputs to our functions, or arguments in our functions. We can just put into this self argument, like kind of hold a placeholder, and then it holds all of them together, and it's easy just to pass between our classes and stuff. And it is kind of advanced TensorFlow, but here we're really just using it in some senses a simple way of using a class, just to be able to kind of keep it a little bit neater and cleaner when we're doing that code. So we're going to create the self one. So we're going to go self, and so in a couple of cases, we're going to do this a whole bunch. So we're going to go self.model, and that's we're setting this to none to get started. But this is going to be our model. It's like setting the attribute model, or the variable model. But now it's going to be inside the self. So we can call and access it, and we can pass it between all of our functions in our class. Okay. So setting the self. So setting the cub, act, pool size, the dense neurons, the dense activation, self dot head, dense neurons, self dot head dot dense neuron activation, the learning rates, and the epochs as well. Self dot. Setting all of those up. Okay. Then what we're going to do is we're going to define model underscore builds. Okay, this is where we're going to build our model. This is what's going to put, I guess, the architecture together. Not going to train it or anything, but set up the architecture for us in our experiments. Okay, so here we're going to do is we're going to do our function that we created, cov block. We're going to be giving this the uncanny inputs, I'm sorry, not uncanny, but the canny inputs, and then a canny hist equalization. These, again, we haven't done the pre-processing yet in our workflow, but we're building the model that's going to take in these two different branches of each one of these. Yeah. So we're going to do a cov block there, and we're going to do a second cov. That's a creation that the function that we created that's going to do two cov layers, a max pooling, and a dropout. Okay. So setting that up right there. And then model builds. And so model build, we're not really going to pass it anything ourselves, but what we can do is we can pass it just a cell. So it's going to be, we're going to have access to all these arguments. We don't need to rewrite this again. So it's just a nice, very handy way to package all of these variables that we're going to need to have access to just in one variable that we can just kind of call it. So we're going to call it, so all we're doing, and this is what's the difference between a method and a function. These methods are part of a class, and they always take, well, you can't see any other ones if you haven't done them yet. They always take and define a function. Another one here is always going to be taking the self argument first to start as we go through this. Okay? So here what we're going to do is, after we build our model, then we're going to be taking tf.keras.layers.latin, and this is going to be next to the output of this second cov block. Okay, we're taking a dense layer here, and we're going self.dense neurons, and activation is self.dense activation, right? Because this is what we have. It's kind of packaged in that little self variable that we have. And then here what we're going to do for the cov block again. The nice thing we did the little function on the left is it's super easy now to do our architecture. Very nice and clean to do something a little bit more complex. We really do have a lot going on, but we made it nice and easy and complex here. Okay. So there are two cov blocks. Then we're going to do a flatten, capital F, flatten layer again. Then we're going to go self.dense neurons, self.dense activation. So we're taking our dense activation or dense layer right here after the flatten right here. So it's cov block, flatten, dense. Okay. After this, we're going to do concatenate layer here, and we're putting these two in a list then of the two outputs, the equalize dense, the canny dense right there. We're then going to do another dense layer after this. Self.dense and ends, dense neurons, and self.head dense activations, right? So we do one dense after each cov kind of series, cov branch, and then we're going to combine it at the end. And there's lots of freedom to play around with this. I limited time to play around with all the different combinations that we could do, so maybe there's a better way to set this up, but I think this worked well. Turned out really good, but I'm certainly sure you can improve on this. Okay. So for our output layer, dense, and just 10 classes of predicting our activation softmax. And really important here, just noticing that I did the names for the inputs and the names for the outputs. Okay, it's really important then, because when I'm going to be defining what goes into what branch, I'm going to be calling on those names and passing in the data. Okay, so set up the model here, set up the input and the output are not the most important, but it's important to have everything, I guess, but setting up the input and the output, right? Paying special attention to that, because what we're going to do is TensorFlow is going to track everything that happens to this, but when we train our model, we're just going to set it up by saying that our input and our output are this, and it will track everything that happens. So we just need to set up a model, to make the model, we just have to. So we're going to do keras.models, and then we're going to do capital. We're going to give it an x, and x is equal to canny input, the dictionary key, and then the input layer right here that we have that's named canny input, and then the same thing for input hist, we do as hist. Okay. Then our y is going to be equal to output and then output. There's no fancy name for that one. Here what we're going to do then, after we pick our model, sorry, after we save or build our model, we haven't fit it yet, but we're going to go self then dot model dot compile. Okay. Set our loss to tf.keras.loss categorical loss. Okay. Let's start left here. So then we're going to go optimizer is equal to tf.keras.optimizer, and here we're going to do add. It's just a good all around. And the thing is, I don't know if it's become my favorite, but I always really start there at least. I'm going to try other ones, but I don't know, it really does work really well. Okay, so the self dot learning rates right there, and then we're going to metrics for our accuracy. So metrics, and then we're going to be making sure that we give this a list. It has S here, so we know that it wants more than one thing. Even though we're giving it one thing, then we need to give it a list of that one thing. Okay. So then what we're going to do here is model. So we're going to define next our model underscore train. Okay. So we're going to be passing this again our self. And then what we're going to do, we're going to be saving to our history object. So we're going to go from self dot model. Compile this model now. To do, so this is turn yellow, so you expect to compile. We're going to go model dot fit. So self dot model dot fit. We're going to be giving it the input and the inputs of our two pre-processing ones that we're going to have right here. Our input and our inputs, or two different inputs from the pre-processing function, and then our output. Okay. Then we're going to do epochs. That's going to come from our self dot yes. Okay. We did a really small validation split. I started a bigger one, but when I was doing for the predictions, I just ended up turning this right down just to make sure I could train off as much data as possible. Okay, so the next one here, what we're going to do is we're going to go dot H. So say that's dot H, and we're going to go history, dot H history, and plot that. And then just as we do this in the loop, usually we're just going to go plt.show. Okay, so then we're going to do our next function, which is going to be model underscore x. And then we're going to be passing this again at our self object. Okay. So then we're going to be doing our pre-processing first. So pre-processing from our function created outside of the class. Then we're going to go self.model underscore train. And then we're going to go self dot. Oh, sorry, the first one's not model train, it's model build. And because we're not giving our build any argument, we're just going to be giving it's nothing, just a self. And here we're going to do then model. It's going to train and then plot each one time of these. Okay, and then in our last one, we're going to do define. We're going to do model underscore predictions. Model underscore predictions. Okay, so we're going to do our pre-processing, and our other pre-processing function again. Do the same thing above. We're going to build. And we're going to do model underscore train. Model underscore train. But after we do that, we're going to get a model, or sorry, self. Because when we train it, remember we're saving the train model into self, so there's no self. So although we're not returning anything from this function, when it's called, it stores something in the self. Okay? And so I'm just noticing here, I'm still seeing this red right here. So I forgot to pass though the self to this function. Then we're going to go model for self dot model dot predict. And we're just giving our prints. Just notice here, it's going to give us a dictionary. We could have more than one predictions, and we would index into that dictionary and get it out based on the names that we're assigning here. So we only have one. We still need to kind of select it out, just like we're selecting out of a dictionary, the name of the key value, which is output here, which is what we're expecting it to be. Okay. And so what we're going to do is tf.arg max. We're going to return that, and we're also going to return self.model in these functions. So C, not seeing any red jumping out at me. Looks good. Let's run this and everything. Oh, that's not the test. Okay. So I won't run this right here, but we'll get it started. So here we're going to be calling as our model class. So a class that we wrote. So it'd be capital M, model, capital E, experiments. Okay. Feels nice writing something with capital letters. It feels important writing your your first class, writing your first class. And then what we're going to do is we're going to be calling from this of dot model experiments. So I'm not going to run this. It's going to run experiments. So notice what I'm doing here, and this was just for I was trying the kernels. Okay. So I went through and tried all of these. I started off, what I did was originally I copied, as we had it here in the function, I copied this, just the function that we're going to pass through it. I have it in the init function. We're going to be giving those. I would put that here in the first place. And I went systematically, one by one, tried the first one, because these are already set, right? So we do have them set up one time in the hyperparameters. But what we're going to do then is we're going to keep all the other hyperparameters the same. We're going to loop through all the possible values of the filters, all the possible convolution, the kernels, the possible ones of these, all the different kind of things. We want to make a list of ALU, ReLU. Here we're just doing simple for the numerical ones. It's easy. We're just going to do from numpy.arrange 2 to 8. And so I tried all the different pooling sizes. So 2, 4, 6, 7, up to but not including 8. And found out which one's the best. So I went and looked, and really the scores were very good. It was very easy to get a good score here. However, getting a good competition, doing well in the competition turns out to be priority because everyone did really, really well. You're really squeezing out like the last little bit that you can do here, but we're going up. We're getting 99% on our validation accuracy. Okay, and again doing really well. Okay, so I just went through and I found really marginally difference, and you're never really sure if the marginal difference you're seeing here is because of just what happened one time, but it was a way to kind of test and keep going through, and then I would, because I'll show you what I do here. I got this started running right now. So we're going to df.values. So let's get this started to run while I keep talking. We're going to do -1 here. So we're going to do the reshape of the test data that we have way up at the top. Okay, and then we're going to do model experiment, and then we're going to do model.predict. So predictions. Okay, model predictions. Okay, so now this will start running here. You can see I set all the hyperparameters right here. All of them, I've tested them, I've trained them. I'm going to do 35 epochs. This won't take too long. So hang out while it starts training, make sure it starts working, and I'll show you the rest of it. So again, I just went kind of systematically through this loop, and it would see, okay, here n is 6. I went through and I found 9.88, no, better, 9.914. Okay, so I wouldn't have thought this, but 7 apparently for the pooling worked the best. Okay, and so I went through systematically. I would find some 99.14, and this again, it's hard to say that this would always work out the best. I'm just noticing right here, I have prediction, model that predicts. Okay, prediction. So I don't want to run the one with the big loop. It takes a long time. Let's see if that works. little experiments. That's so much code writing truthfully, so it's not surprising. You know, say it would be nice to never get. Okay, so I figured out the little mistake that I made. And what it was actually pretty simple. So we see in this tf.keras.models.model. So we build the model up to the input and outputs. It must have worked by some weird reason that I've done this first. So it was originally the way I had it set, and I didn't change this to none. This is just how it was left. So it worked for me at one point. How it did, I'm not sure, but what it is the x and the y. It actually needs to be in this. I don't normally always do this. I didn't know why I said it was x and y here, but it should be inputs and outputs. As it can be many of them. We have a dictionary, so a collection of variables. So if you run that, and then you run, stop this just to show that it works. So stop this one. If you ran that one up above, let's run this one, and then what it will do is this will run fine. So that was all it was. It's gonna be super minor. That's why I didn't understand X. This is really in when you're doing the model, like the build, you're building in with the inputs and outputs. It should be inputs and outputs that you're putting in. Okay. So we'll let this train. We'll get started on the rest of the stuff while this is going. So we're going to go dfpreds. We're going to put our into a PD series the ins test, the indexes that we have from way up above, and the predictions that we get from this function right here. We get our preds, right? We've done the argmax, so put it back into one column. Okay. Then we're going to go from this data frame that we create from that. We're going to go dfpreds.columns, image ID, label ID. We save this to a data frame. And again, this is connected to my Google Drive, so this is my file path to get this in there. You'll have to do your own. And then just in this next one right here, we're going to do tf.keras.utils.plot underscore model. Okay, and that will give us this cool model output right here. We get the input layer, the convolution, max boolean dropout, convolution, boolean max dropout. So two blocks right there, flatten, dense, concatenate, dense, and then our output there. Okay, so pretty cool little model that we end up having at the end of this workflow. So thank you. Let's see how we're going through there. And you can see we start to get up to 97 really quickly. And I don't know if there's a solid way. So what you'll find is after you do this, you print right here, and you can go to this page at the very top. There's collections right here, which is this page right here. You go to submit predictions, and you drag and drop the file. So I've been copying this one right here. I have the predictions right here. So if I download that, and then I can upload that to submit predictions, browse file, go to my predictions. I'm pretty sure I submitted this one already. I don't think this is the winner one, the best one, but the best I've gotten is 99.067, which is normally a prediction. For this contest, I actually didn't do that well still. I did okay, I guess. Yes, there's the same one. Let's go to leaderboard. So you can jump to your scores right here and see. So I'm 646 out of it's a pretty big number, truly. It's 1600, so top 28% or something like that, 29%. Nothing special. Truthfully, I think there's a lot more to be done with this, but really the margin for error, you can probably find that training the exact same model, same architecture, will give you a slightly different score, and that little margin of difference might be enough to push you up and over. Sort of thing. And you can see lots of these people tried. Some of them no, but lots of these people tried 10 times, and you'll see as you track with more scores, there's quite a high number. Some people got perfect. Not many people though. Okay. So thank you very much for joining me today, and I will see you next time.